Hello, everybody. My name is Dan Chen, and today I'm going to introduce you about the diagrammatic representation of the perturbation theory, especially for the multimode systems. And this video is recorded for the midterm presentation for the network course I studied this quarter. So here is the motivation. As a PhD student studying quantum computing, this is the roadmap of it in my mind. So nowadays we are already able to fabricate a qubit inside a single mode. However, such a qubit may suffer from experimental noises, environmental noises, and decoherence. So the idea of error correction is to store a bit of qubit into multiple modes so that we can correct the dominant error that exists in a single mode qubit. So here is an example. We store the information into a cavity and use an ancillary qubit to correct it. Or we can store the information into multiple qubits so that those qubits are error protected. So, and here is the perturbation theory probably useful for studying those multimode systems. If those modes are dispersively coupled, which means that the coupling strength is much smaller than the energy difference between modes, then the perturbation theory is valid. The general form of the Hamiltonian is, of course, the bare terms H0 plus the coupling term, which is pretty small. And by perturbation theory, we can study the eigenstates, which are also named as dressed states. We can also study the eigenenergy and control operators matrix element, etc. And here, I will give a quick, simple example of a qubit resonator coupled systems. And the Hamiltonian is still equal to H0 plus V. And for H0, it is consists of a resonator mode and a nonlinear qubit mode. For a qubit, the energy structures usually looks like this. And if we consider the bare state in different resonator state manifold, we can imagine that there are multiple copies of it. And this is the whole spectrum, what the whole spectrum look like without coupling. If there exists a coupling Hamiltonian, which will look like this, then those states are connected. According to perturbation theory, the eigenstates are very close to the bare tensor product state up to a small corrections, and the eigenvalues are very close to the sum of the bare energies up to a small perturbation. And we can also understand this level structure as a network. So we can represent each bare state as nodes. As I represented here, there are nodes representing different bare states, and there are infinite copies of qubit states. And for each of the nodes, they have energies or bare energies equals to the sum of the bare mode energy. And the link between nodes M1, M1 and M2, M2 are simply described by the coupling Hamiltonian. And they are represented in the figure like this. The links are undirected, but weighted. The weight of the link equals to the matrix element of the coupling Hamiltonian. And finally, we can use the perturbation theory plus the graph to study the energy correction and state correction of different levels. Say if we want the energy of the state, eigenenergy of state 0, 1, we can write down terms related to all loops that starts and ends at this state. For example, if we consider the second order, which is a loop consists of 2 steps. So for example, this one is a possible loop, and that one is also a possible loops. And the terms related to those loops are simply weight square, or the weight of the link squared divided by the energy difference between the connected states. And for this 4th order, we consider the loops with 4 steps. And for example, this one, if we do the back and forth twice. It is a 4-step loop. And for example, this is also a 4-step loops. Here are more examples and more examples. And finally, the fourth order perturbation is simply the product of all the weights divided by the product of all the energy differences. And note that do not miss some of the loops, and we should count all the we should take all the loops into account. And we can study the state correction in the same manner. And for this 5 minutes video, I won't elaborate here. And thank you for listening.